We are Group 9 and our assignment topic is credit card default. Our dataset containing 30,000 records from a Taiwan bank in 2005, and the goal of our analysis is not to build the most accurate model, but to demonstrate how data preparation decisions affect model behavior. I'm Huang Shuyi, responsible for sections 0 to 3, dataset governance, profiling, cleaning, and encoding. Before touching the code, we should ask two questions. Who should be allowed to see this data and for what purpose? This dataset contains 5 attributes that carry PDPA sensitivity. ID is a direct identifier and must be dropped immediately. Sex and marriage are protected characteristics that using them in a real credit decision system could result in discrimination, regardless of their statistical predictive value. We document this explicitly as a purpose limitation. In any production deployment, sex and marriage should be excluded. When we previewed the dataset against its original paper, we found 4 documentation gaps. The first is education. Education is documented as having 4 categories, but the data contains values 0, 5, and 6 that the paper never defines. Second, marriage has an undocumented value 0. Then, the pay repayment columns contain values -2 and 0, which are completely absent from the paper's measurement scale. Finally, the column Pay1 is referenced in the variable naming convention, but is entirely missing from the dataset. Critically, its null function returns 0 for all columns. A naive check would declare this dataset clean. These issues are invisible to standard missing value checks, and they only surface through structural profiling. This is a real data governance failure that the data and its documentation are inconsistent. And it demonstrates exactly why profiling cannot be skipped, even with published academic datasets. Layer 2 and 3 confirmed 2 more structural issues. The financial columns show severe right skew, which directly influences our choice of scalar later. The correlation matrix reveals that bill amount 1 through bill amount 6 are interpolated above 0.9, indicating multicollinearity. We flag this here and leave it to address through feature engineering. We also confirmed a class imbalance of 78 to 22, which motivates smooth in the modeling stage. Section 2 is about choosing a reasonable way to clean data. For education and marriage, we chose the paper's defined catch-all category. For the pay columns, we treated -2 and 0 as equivalent to -1, which means pay duly. We also found and removed 36 genuine duplicate rows. Crucially, the train and test split was performed before any encoding or scaling to prevent data leakage. In Section 3, every encoding and scaling decision was made with explicit justification. Marriage gets one hot encoding because it is nominal, and label encoding would falsely imply an ordering between married, single, and others. The financial columns get robust scalar because they are severely right-skewed with extreme outliers. The key principle is that feed all scalars and encoders on training data only, then transform the test set. We should note that robust scalar preserves the shape of the distribution and the right skew remains visible in both histograms. This is basic and correct because scaling changes the unit of measurement, not the underlying distribution.
My part covers section 4 and 5. I start from the target distribution. Only about 22.1% of clients defaulted, so default is the minority class. This matters because both EDA and model accuracy can look acceptable at the surface level while still hiding the real credit risk problem. My focus is age. It first looks meaningful, but the conclusion changes after controlling for limit balance. In bivariate EDA, limit balance is the clearest signal. The default rate falls from about 31.8% in the lowest credit limit band to 14.7% in the highest band. Age also seems related, but the pattern is not clear enough. So instead of trusting the age bar chart directly, I check whether limit balance is affecting the age pattern. This is the Simpson's paradox result. In the aggregate view, 20 to 29 look riskier. 22.9% default compared with 20.3% for 30 to 39. But after controlling for limit balance, the result reverses. In every credit limit band, the 20 to 29 group has a lower default rate than 30 to 39, so age alone is misleading. Limit balance is the confounder. This heat map explains why the reversal happens. Younger clients are concentrated in lower credit limits. For the 20 to 29 group, 35.5% are in the lowest limit balance band. For 30 to 39, only 16.8% are there. Because low limit balance has higher defaults, the aggregate age result is partly a composition effect. The model results show a similar risk. The dummy model has acceptable accuracy, but default recall is 0, so it misses all defaulters. Balanced logic regression has lower accuracy but higher default recall and lower business cost when missed defaults are expensive, so accuracy alone is not enough. Finally, bias analysis is a governance check. Sex and marriage can help audit fairness, but shouldn't be automatic prediction inputs without justification. Also, the dataset only includes accepted clients, not all applicants, so selection bias may exist. So my takeaway is control confounders, evaluate minority errors, and audit sensitive variables.
Hello everyone, my name is Shi Chen, and I'm responsible for section 628. My part focuses on feature engineering, model comparison, and final interpretation for credit card default prediction. The main challenge is class imbalance, right? Most customers are non-default, so a model can achieve high accuracy by predicting no default most of the time. Because of this, I evaluated the models using not only accuracy but also core precision, advanced score, PRAUC, and confusion metrics. In section 6, I created 4 behavioral features. First is the average payment delay, which measures the average repayment delay. The max delay captures the worst delay across 6 months. The oscillation rate measures credit usage relative to credit limit. Finally, the repayment trend shows whether repayment amount increases or decreases over time. This feature makes the model more interpretable, and I also dropped the highly correlated VLMT columns to reduce the redundancy. In section 7, I compare 4 pipelines using the same split, the same test set and the random set, which is equal to 42. Pipeline A is the minimal logistic regression baseline. The pipeline B is the feature engineering and pre-processing. Pipeline C is smooth to improve minority class detection, and pipeline D uses a decision tree with mode to test a nonlinear model. The key point is that each pipeline has one major change, so the comparison is controlled and easier to interpret. The results show a clear accuracy paradox, right? As you can see, pipeline A has around 77.9% accuracy, but its recall is 0. This means it detects no default customers at all. Pipeline B improves overall performance and gives the best precision and AUC scores, but its recall is still limited. The pipeline C gives the best recall and F1 score. Its recall increases to about 0.598, so it detects many more default customers. The trade-off is lower precision because it also produces more false positives. Then the pipeline D is useful as a nonlinear comparison, but in this experiment, it does not outperform pipeline C. So if the goal is to catch more default customers, pipeline C is a better choice. Okay, the confusion matrix makes it easier to see. The A most predicts everything as non-default, so it fails on the minority class. Pipeline C and D detect more actual defaults, but they also increase the false positives, which is FP, right? So as you can see, the precision recall curve is especially useful here. Because the default class is a minority class, it shows the trade-off between catching more default cases and keeping prediction precise. To conclude, I have 3 takeaways. First, accuracy alone is not reliable for imbalanced accredited default prediction. Second, the feature engineering helps convert monthly repayment records to clearer behavior signals. Third, the smooth improves recall, but it is a trade-off rather than a free improvement. So for this project, I recommend pipeline C when default detection is a main priority. For real development, sensitive variables such as sex and marriage should also be reviewed carefully for fairness. So that's all. Thank you.